me, I will start by introducing our speaker. And in fact, the topic today, solid state batteries. Well, lithium-ion technology powers the growing number of battery electric vehicles on our roads today. It's reliable, it works well, but ranges are still not the same as their internal combustion engine counterparts. And of course, recharging can take many hours. So today we're going to consider whether the latest solid state battery technology could address some of those issues. And our guest today, Dr. Yunlong Shao, is Assistant Professor in Bioelectronics and Energy Storage at the University of Surrey's Advanced Technology Institute. He also holds a joint appointment at the UK's National Physical Laboratory as a senior research scientist. So Yunlong will be covering the development of solid-state batteries, together with the different types of electric vehicles and their specific battery performance requirements. So putting those two things together, he'll explore the prospects and challenges of adopting solid-state batteries in electric vehicles, but also other applications where batteries are used. We're very fortunate to have Yunlong with us today. His career so far has taken him from universities in Wuhan, China, where he focused on electrochemical energy storage and electrochemical probing, to Harvard in the US, where he conducted research in nano semiconductor devices and flexible electronics for electrophysiology and nanobio interfaces. His passions are understanding and optimizing electron-ion transport in energy storage systems, the electrical, chemical, biological signal processing at the interface between electronics and biological systems, and using micro and nanoscale materials, biosensors, and their integration in flexible electronics. And so far, his work has been published in over 60 peer-reviewed journals, such as Nature and Nature Nanotechnology. So let's now learn more about solid-state batteries and how they may become commonplace in vehicles and other energy storage applications. So it's over to you, Yunlong.
All right, thank you very much for the introduction and the invitation. So it's my pleasure to join this webinar and also share my recent my experience about the solid-state batteries and electric vehicles. First, I have to explain. So this is according to the audience. So this is very general, like presentation lecture. Is not for specific experts. So I just give a very brief background to the general peoples. So hopefully, can get some like overall feelings about the solid-state batteries for and for the electric vehicles. And if you have some additional questions, I'm very happy to answer after the presentation. And also, I put my email address here. If you have any questions you want to discuss separate individually, so feel free to send me emails. So yeah, today's talk I will introduce about the solid-state battery powered electric vehicles. Is that possible to go further, drive safely, and charge faster? So here is the outline of the my talk. First, I will introduce the background of the electric vehicles and the battery performance requirements for electric vehicles. The second part will be the the development of the lithium-ion batteries, which is already commercial and being widely used in the electric vehicle batteries. The next part, we will talk about the solid-state batteries, especially talking about the opportunities and the current challenges, as well as how to solve those challenges of the solid-state batteries. And the last, we'll give a quick summaries. Yeah, first, look at let's introduce the background of the electric vehicles. So first, I just found a very pretty good videos showing why the history of the electric vehicles and why we need to use electric vehicles for ours, not only society but also for the environment. And yeah, let's have a very quick look of this video.
As concern for the environment rises, we are seeing increasing demand for electric vehicles. Though EVs today are presented as new innovations, the fact is that such cars go back around a century. While there's a dispute at what point in history EVs were born. We can take 1828 as our starting point. That's the year in which Anios Istvan Jedlik made the first electric car. Back then, it was in the form of a model. Perhaps that is why many histories skip that contribution. Rather, they take 1834 or 1835 as the year in which electric cars were born and give credit to an American, Thomas Davenport. It was then that Davenport built a small locomotive that was powered by 2 electromagnets and ran on a track. A few other inventors dabbled with electric cars during that decade, and the peak of the electric car is considered to be about 1900. At that time, electric cars made up about a third of all cars manufactured in the United States. However, by the 1920s, electric cars would stop being commercially viable as gas power became a lot more accessible, and people wanted vehicles that could go longer distances and had more horsepower. Henry Ford dominated the car industry beginning in 1908 with his mass production of gas-powered cars. For over 60 years, these cars continued to advance. While gas was plentiful and inexpensive, people were content with their internal combustion engines. But by the late 1960s, there was a change. Gas prices started to climb steeply, and there was the beginning of concern over air pollution. Congress introduced the first bills promoting EVs in 1966. Spurred on by the rise of government regulations, American car makers tried to integrate electric power in cars in the form of hybrids. But the real revolution in the field came out of Japan. Toyota introduced the Prius, the first commercially mass-produced and marketed hybrid car. It was a hit from the start, with close to 18,000 units sold the first year. Then other manufacturers entered the arena, most notably Tesla. In 2006, the firm unveiled the Tesla Roadster. While in 2009, GM released the Chevy Volt, which marked a first for plug-in hybrids. The technology used in its battery was developed by the U.S. Department of Energy. More importantly for the electric car market as a whole, the Department of Energy invested in the batteries used for such cars, which reduced the price by half over the earlier part of this decade. By 2014, there were 23 plug-in and 36 hybrid car models on the market. That number has grown with contributions from automakers around the world. And new models billed as competition for Tesla come out every year. The EV world is rising. Are you prepared for what's next?
Okay, it's a short videos from the interest in engineering. So it's covered the history of the electric vehicles as well as like the reason for of the reason of the electric vehicles. So electric vehicles, or sometimes we call it EV, so it's used one or more electric motor, and for the electric EVs, it's not only including the electric cars, it's also including other vehicles, or for example, even underwater vehicles or aircrafts. And those the powers not only from the batteries, it can also from other, for example, solar panels or other like electric generators. But when we talk about the electric EVs, we usually in our daily life, I think we mainly think about the electric cars. So this actually this is a very big market. You can see from these figures, like it shows like 3.1 million EV was sold last year, and it's increasing dramatically. You can see now we are here, and you can see like it's the overall cars like is maintains like stable, but if you look at the ratio of the EV, the percentage increase a lot. Maybe after a few years, they can dominate the market. So as the video shows, like they introduced several types of EV. So classically, it was classified by 3 types of EV. One is a hybrid EV or hybrid non-plug-in EV. The second one is plug-in EV, and the third one is a battery electric vehicles. Sometimes we call it BEV. So I know there are some additional additional type, but the main categories, they are these 3. So the hybrid EV, you can see from these pictures, it contains like the gasoline engine and electric motor. So it also have the gasoline engine here and also the battery here. So this kind of hybrid EV, so the batteries was used to absorb the regenerated braking energy and also to support the accelerations. So you already have a quite small battery pack size. You can see here is a medium, and the battery was not charged by external electricity, but it was charged by the braking energies. So this is a hybrid. This is a hybrid EV, and another one is a plug-in hybrid. So plug-in hybrid, this battery is not only used for support accelerations, it can also used as a primary power. Actually, when we drive this kind of plug-in EVs, so we just use at the beginning, if the battery is full, we just use the batteries. But if the battery is running low or like out of the power, then we can switch to the IC engine and use as, so which means the gasoline engine is used as a backup supply. So this kind of battery is larger than this one. So, and it was not charged by the internally, but it was charged by a plug-in. So we can just plug in and charge like at the station. So the last one is called a battery EV, battery electric EVs. So you can see from these figures, there's no gasoline engine anymore. So they're only electric drive. So the battery pack could be very large. Some brand, for example, the Nissan Leaf, the Tesla Model S. So that are like very typical battery electric vehicles. They provide solar power and energy resources. And you look at these figures on like you can see like all the battery EVs, there are no emissions, and the plug-in have a little, and hybrid have even more, and conventional like this is just our petrol-based or diesel-based. So here is the data shows like the UK electric car markets. You can see right now, this is the data is from last year. So you can see right now still have half like cars was sold based on the petrol based, and 16 like diesel based, and the electrical cars, they are totally around the 25, and you can see the battery EV is 6.4 and plug-in 3.3. Hybrid non-plug-in, they are like around 17. So even, but if you look at the growth speed, you can see the battery EV and the plug-in battery EV, they are growing very fast. So, and you can see the conventional one, they are even decrease. I think there are a lot of reasons to like behind. So from the manufacturer reasons, I think one big reason is the overall cost is have been reduced. But even that was the battery, the overall cost reduced. You can see the full battery EVs, they are still have a very is still much like expensive than the conventional or the plug-in. So if you look at this is the overall price for one electric vehicles, and this color, different color shows the price for different components. And the blue one, that is the batteries. So you can see for a battery EV, the main part, the main cost will be the batteries, which means the biggest challenge for the mass market uptake will be the battery cost. So this is just from the manufacturer point of view. And what it will from the end user point of view. So the auto price, they have like questionnaires, and they found from the end users why they choose the driving, why they choose driving the electric cars, or why they don't like the electric cars. So first one, the pros, definitely like it's environmental friendly, and also they have some discounts. For even though it's cost a lot at the beginning, but it's have a low running cost, and also have some tax benefits, and also quite comfortable, and have a very fast acceleration. But a lot of people, they haven't considered this because of following reasons. They can't find some like a lot of charging point, especially they are not driving in the cities. If they are driving in the urban space, it's quite difficult. Also, the charging times, like right now, it still takes like 7 hours or even over 10 hours to charge the battery from empty to full. And also the battery range, right now about the average electric car range around 200 miles. But if you want to like driving even longer, then that will be a problem. The purchase price, as shown in the previous slides, electric vehicles still have a higher price compared with the traditional one. And next one will be the safety concern. So there are a lot of news come out every day, not every day, like sometimes talking about, oh, the batteries like catch fire, or the electric vehicle catch fire. So which like make people feel like this is a dangerous like vehicles. And also some people like they like to enjoy the like driving, even not the automatic one, even they like driving the manual one. So they think like driving electric cars have a less fun. That's understandable. But if you look at all those 6 reasons, 5 of them are related with the batteries, like battery, especially related with battery safety, battery charging speed, battery like energy and power density, right? So let's look at what make up an electric vehicle batteries. So currently we just use the lithium-ion battery lithium-ion batteries as vehicle batteries. So initially those batteries will be assembled into a cell type. They can be cell type. Yes, they can be assembled into a punch cell or cylinder cell, shown like this. And then a lot of like this single unit cell will be assembled into a module. This module will connect it with some additional mechanical support, and also some thermal interface, and some additional terminals. And then this module will be further assembled into a pack. So in the pack level, so they can be used directly and transferred directly in the electric vehicles. And at the pack level, they have some additional like electronics. For example, they have some battery management systems. They have different kind of sensors, controllers. So and also have like even better like packaging productive materials. So this slide just shows like what's where should the electric vehicle batteries be in the next decades. So this resources from the Friday Institute. You can see right now this well addressed like currently end user like concerns. For example, they want to reduce the cost of battery from this number to here. I won't read in each one, but you can see from here. And the inner densities increase like almost double the inner densities from now to maybe 15 years ago, after 15 years. And the power density also like not only doubled, even increased 4 times. The also definitely increase the safety and the lifetime. From now, we after like if you driving electric vehicles after 80 years, maybe you have to replace it. But at 2035, we just want to the batteries like drain like continuously, maybe their lifespan like can double, and also the temperature issue. So now if it's, I think UK is fine, but in some very cold or very hot areas, so the battery will have some additional issues. So now we can the battery can run from -20 to 60, and then we also want to increase this range, and also we also want some additional parameters such as predictability and also recyclabilities. So this is some background about the electric vehicles, just a very brief background and the performance requirements. Then I will talk about a little bit more details about the lithium-ion batteries. So I will not go into very details, not very like a lot of material science and chemicals, no, just a very brief background. So this is a conventional lithium-ion batteries. You can see the lithium batteries. It have a like anode, have an electrolyte, and in the electrolyte you already have a separators, and then is a cathode. So this is just to show the 3 key components. You can imagine there's some additional others like components such as the case, the current collectors, but it doesn't show here, and it won't affect too much about the performance of the batteries. So right now, for the conventional current or commercial like lithium batteries, the anode there we usually use a graphite anode, and for the cathode, depend on the usage. If for the electric vehicles, we usually use the lithium iron phosphate, but if we use, for example, in our computers, in our phone, that will be the lithium cobalt dioxide. So I will explain the reason. And for the electrolyte, right now, most of the electrolyte still like is an organic liquid, is a mixture of a liquid lithium salt in an organic liquid solvent or a polymer gel, and the voltage will be 3.6 to 3.8 volts. So here just shows different kind of materials, including a lot of cathode and a lot of the anode. So you can see this is a graphite. Is here it shows the specific capacity, and here it shows the voltage. This is the graphite, and here shows the lithium iron fluoride and the lithium cobalt oxide. So and the voltage is dependent on, you can divide by the gap between these two voltage, and with a voltage and with current density, you can get the energy density. So here just shows how like a picture shows how the lithium battery work. So here we just assume the cathode, the lithium cobalt oxide, and the anode is graphite. So you can see during the charging process, a lot of lithium, they will diffuse from this lithium cobalt oxide to this anode, to this graphite side, and the reactions just shows here. This is a charging process. This is the reaction happening on the anode, and this on the cathode. And also externally, the electrons will transfer from this cathode to the anode. And during the discharge process, so everything is reverted. So you can see the lithium diffuse from anode to cathode. This is why it looks like a rolling chair. So just like going up, like up and down. So this is why we also call this kind of battery as a rocking chair mechanisms. I just want to explain. So this mechanisms, or this schematic is shown just based on this cathode and anode. For there has some additional other type of cathode and anode, they have the different reaction, for example, some conversion reactions or alloy reactions, and there's the schematics may not be same. But this is just a commercial battery, so the battery we used, this is based on this reaction mechanisms. So a brief talk about the anode, and as I said, right now the graphite are used as the anode. It was used as anode because first it's quite cheap, it have a high abundance, and also it's have good electricity, electric conductivities and thermal conductivities, and also it's electrical passive, so it also means like corrosion resistance. This is why it have been used as anode, but it also have some limitations. For example, you can see there have like a lot of carbon atoms here, and 6 carbon atoms can accommodate only 1 lithium, which limited their capacity, theoretical capacities, which is this number. So because that is also because of the low density, so it also have a low volume capacities. This is one of the limitations. So another limitations is before explain another limitation, maybe let me first explain what the solid electrolyte interface mean. So when we charge the batteries, you can, as shown in the previous slides, so the lithium will diffuse into this into the carbon, and this become a charged or lithium the carbon. So this is a highly reductant agent. They can reduce some electrolyte, liquid electrolyte into other components. For example, they can into some solid components, and these components can attach on the surface of the anode. So we call this layer as a solid electrolyte interface. So shortly as SEI. So this things can be generated, and it can protect some corrosion reactions. So if that was uniform, but it may also generate some problems, which just shows here, especially when we charge the battery at a very high rate. A lot of the lithium metal that they can also be generated. As I said, like the lithium metal, they come from the electrolyte containing lithium salt. So they can also deposit on the surface of the graphite or in this SEI, and they can even growing into a dendrite structures, and sometimes they can become a dead lithium, which means they can't convert into the lithium, come back to the electrolyte. And this dendrite dead lithium, they will lead to the capacity loss. And also, as I explained, so this dendrite will grow, this lithium will grow into a dendrite shape, which means sometimes they can grow even like over the separators, and from the anode side even tied to the cathode side, which means the battery will be shorted internally. And because of that, the battery probably will have some problem, especially if we are using some organic like electrolyte. It has the potential to catch fire. So this is just the anode side, and here is a cathode. As I have already shows, this figure shows different of the cathode here. And commercially, we use the lithium cobalt oxide and the lithium iron fluoride, and there also have some additional other type of cathode. By the way, the lithium titanium oxide is usually considered as anode, especially the NMC. That is the lithium. It shows here is the lithium, manganese, cobalt, nickel oxide. This shows a large, very promising parameter performance. You can see from here they have a very good performance, very high specific energy. The cost is at average, not very high. They have good lifespan if you consider compare with the lithium cobalt, and very good safety, and also the performance is very good. So I think people already consider this, the NMC, as a promising even next generation cathode candidate. So another component is the electrolyte. So currently we just use a liquid containing electrolyte. Just it shows like here, you can think this is some liquid particles, and here are some other hybrid particles with lithium salts. And another kind is gel polymer electrolyte. And beside this, we also sometimes for the research or for some specific small devices, we can also use a liquid electrolyte, but that is not like it's quite expensive and usually not used in the widely. So besides that, we also have some dry electrolyte, especially some solid polymer or inorganic solid polymer electrolyte, which I will explain in the next few slides. So that is just to go through very briefly about the anode, cathode, and the electrolyte. So this just shows like the options for future lithium-ion batteries. So right now, just I guess from two resources. One is from the Nissan. So from their point of view, they think right now we just trying to develop maybe in between these two range, but in the futures they are more prefer the high performance nickel NMC materials or even sulfur materials. And for the electrolyte, right now I think they are targeting some polymer based, but eventually they want to become solid and organic. For the anode, right now commercial is graphite, but now they have already put additional like high energy anode materials, for example silicon, into the graphite like structures. Even though at the beginning maybe it's still graphite dominates, but eventually want to use silicon as a dominant anode, because if you look at previous slides, so the silicon have a much larger like capacities compared with the graphite, which means you can, if you want to provide the same energy density, energy of the battery, so you can put less, or if you put the same amount, you definitely can provide a longer, like larger capacity. And also increase the voltage. So this is just from the company's point of view. So from academics, we are even thinking like some more aggressive, more advanced. Right now, even thinking about using some ultra thin lithium metal. So as the anode, because the lithium metal, you can see they have even larger capacity, and also use a safe electrolyte. Safety electrolyte, especially using the solid state electrolyte. Yeah, this is just some options for future lithium battery. And in the next part, I will just introduce about the solid state batteries, because here already both of them shows like using the solid and the safe electrolytes. So let's look at what the difference between the solid electrolyte, solid state batteries and conventional lithium-ion batteries. Actually, the solid, when we're talking about solid state batteries, we think, oh, that was an emerging thing since this was generated in the recent several years. But if you look at the history, actually, it's already developed for over 50 years. The first one even developed like in the late 1950s. So, and also that have been widely used, not for the lithium, at the beginning, not for some lithium batteries, but that can be used in the high temperature sodium sulfur batteries, especially using, for example, the aluminum oxide in the lithium sodium sulfur batteries. And later they have been widely gradually used, but the performance at that time, at the early age, was not as good as right now. One big reason is conductivities. So the ionic conductivities, so the ionic conductivity is relatively low, and there have a lot of problems like the interface issues, which we still have those issues, which I will explain later. And because at that time, when we use the solid state batteries in lithium-ion batteries, the performance usually relatively weak. But recently, because the new type of the solid state electrolyte was developed, then the solid state batteries have become very hot topics. So here just shows like a lot of different type of the solid state electrolyte materials, organic, oxide like sulfide, even polymer based, like there are 6 kind of different solid electrolytes with different parameters in like either chemical or thermal stabilities, etc. If you are very interested, you can read this paper, very nice review papers. So yeah, here is just the solid state batteries, main industry players. So right now just shows like, for example, I think right now the North American, like Asia and the like Europe, they are still like have several very important industry players in the solid state batteries field. So what's the advantage of the using solid state batteries? I think as I just shown, if we just use conventional batteries, we will use the organic electrolyte. That organic electrolyte can very easily to catch fire. But if we just use organic electrolyte, especially all solid state and organic electrolytes, then they won't catch fire. They are non-fireable systems, right? Everything is just a solid state. And also, if we can, they can for the conventional, you can, if you remember, they have separators and a lot of you have a large volume electrolyte. But if you just use a solid electrolyte, then you can make a battery very densy. So which means it have potential to have a high volume energy density. And also, as I mentioned, like the anode side probably can generate some lithium dendrite, and they can penetrate this separators. But solid electrolytes, initially people think they can fully suppress the dendrite, but after some recent study, they found they can still partially suppress the dendrite, but this still be a problems. By the way, when I talk about this kind of batteries, it's I'm introducing the particle electrode. I mean, like the materials just used anode or cathode materials. It just has some large particles. They are assembled into the electrode and then into the batteries. There are another type of electrode called the thin film electrode. So this kind of batteries, they can they can also be fabricated into the solid state thin film batteries. So everything, they can be evaporated by, for example, by sputtering, even including the anode material, cathode material, and the electrolyte. So this, and they are quite thin, usually from like hundreds nanometers to like even several microns. So they have very short like ion diffusion distance and have very good like adhesion between the current collector, between this very smooth interface. But when we're talking about the batteries for electric vehicles, we are not talking about this, because this is just designed for some specific small chips or some flexible chips. They are used for some different kind of electronics. And if we want to become a large scales, making large scale batteries, big batteries, like we are still talking about the particle electrode. And in the few slides, I will explain some challenges and about this solid state batteries. They are I mentioned is this kind of particle electrode, or like these structures. So actually, there still have a lot of challenging in the solid state batteries. This is why it haven't commercial, and especially you can imagine if we are using all solid state electrolytes, the main challenge will be generated at the interface part, at the electrolyte and the anode interface, or the solid electrolyte cathode interface. For example, you can imagine if this solid interface, then it have very poor white stabilities between your anode and the electrolyte. Also, if very good SEI, they can protect the materials. They have a very good cycling performance. But sometimes, because it's some better interface, they can have generate some undesirable, like SEI, and also still dendrite growth. I will explain later. So yeah, this is still could be a problem for the lithium, for the solid state electrolyte, especially if you are the electron conductivity is high. So this is related with anode side. With the cathode side, there have some creating some strain crack, and this is a cathode electrolyte interface. So similar to the SEI, so we call it CEI. So those issues are generated at this interface and could lead to some per rate performance, reduce the cycling performance, and also could lead to some safety concerns and even poor cycling performance. So because of time limit, I can't go through one by one. I just pick up several most serious issue and also explain the reason as well as how to solve these problems. So the first one is the solid contact. Especially if you don't add a little bit liquid electrolyte, if you just use pure solid, then that will be a problem. You can imagine there are some porous structures with was not contact directly. The materials was not contact directly with the electrolytes. So then that can especially if you can only charge if you use a high current density for charging and discharging, the electrons or ions can only go through the ions can only pass in the specific areas, not everywhere. So then can cause some rate performance issues. So one of the most powerful tools to improve the readability of the interface contact is interface engineering. So for example, we can use some ALD to create some interlayers or some additional artificial, doing some surface coating to increase the readability or to fill in these porous structures, then make it become smooth or increase the readability. In that case, they can have a lower resistance interface. You can see this is just after surface coating. If they use a lithium metal as an anode, then the contact angle have significantly reduced, showing a better readability. Another challenge is dendrite growth. So recent research have also found ideally the solid electrolyte could allow the lithium diffused but stop the electrons. But some recent study found the solid electrolytes, still have a very, very low, but still can have some electrons pass through, which means they can also create this lithium can create some dendrite growth, and those dendrite they can even lead to some failure of the solid batteries, especially if we use some large current. This kind of phenomena was even more serious. So also surface engineering, there are a lot of strategies to overcome these issues, and interface engineering. For example, we can introduce an artificial artificial layers, artificial SEI, or introduce additional layers that allow the lithium-ion diffusion, but stop the electrons penetrate. That could be very useful and to avoid this kind of situations. So another challenge is electrolyte or the volume, electrode volume change. This could be also generated by the dendrite growth. If the dendrite growth inside of this, by the way, this is just some images shows the solid state electrolyte after cycling. So you can see there are a lot of crack inside, which also, if with a lot of crack, then the performance, especially the ionic conductivity, will dramatically decrease. So this is because maybe the dendrite growth or the anode or cathode electrode materials volume changes, they can create some pressure and then can lead to this kind of crack. So there are a lot of also have a different kind of strategies, and one strategy is doing some like mechanical engineering. So this is our recent work that recently just submitted. We can introduce using some ion implantation method to create some pre-strain, and then they can stop make the solid state electrolyte like pre-strained solid state electrolyte, which can overcome this kind of situation to stop and also stop this dendrite growth, make it cycling longer cycling performance. Okay, so that is just some advantage and also some disadvantage of the using solid state electrolytes. And as a summary, so back to the title of this talk, will the solid state battery powered electric vehicles go further, drive safely, or charge faster? So I think from my point of view, so I think it definitely can be drive safely because you don't have a lot of flammable materials. But if at current state, we still have a lot of challenges need to solve, especially like the bad interface. Because those interface issues, right now we can't use a high current density. So if we compare with the traditional current lithium batteries, the current density used in the solid state batteries is still lower than the current this kind of conventional lithium batteries, which means at its current stage, unfortunately, we can't see that can drive charge faster. So can it go further? Possible if we just thinking about the it have a because they have a high potentially they have a high volume energy densities. So this is just from my point of view, this just figure just shows current battery type and the future solid state battery type. So but if all those problems have been solved, then I'm sure they have a huge potential to use as in the electric vehicles. All right, that's it for my presentation. So very quite general. I don't want to go to very some specific, very deep, but just for some very general background introduction. Thank you very much.
It raises so many questions, and not just from the audience, but from me as well. And one of the things I was wondering about was it seems very much that you are working at micro and nano scale with the technology. So how practical is that to work within a lab? Because it seems like a lot of this would benefit from a very highly mechanized manufacturing process, which when you're prototyping things, I'm sure is impossible to do. So how do you experiment in a meaningful way with something that could later be put into production?
Okay, yeah, thanks. I think to improve the battery performance and to develop the solid state batteries, we can do a lot of challenges can be solved at the lab scale, and then there have some engineering challenges can be solved in maybe in some manufacturing or some larger like lab from the industry point. But from the lab views, I think, for example, we can develop different kind of materials, and we can even as I just shown in the slides, we can just do some interface engineering. We are not making a large batteries. I know a lot of different other groups, they have the capability to making this large batteries, even punch cells. But for us, if we just focus on the electrode interface point, and we can make a small different deposit different materials or using ion implantation method. We have at Surrey, we have very nice ion UK ion beam centers. We can do a lot of ion implantations. So that sense is very difficult to. So it's sorry, there have a lot of different parameters we can try, and then we can apply those. From my point of view, we first fabricate some nano devices. We can even use this optimized strategy in our thin film batteries. And we found that as the thin film, use the thin film batteries as a platform, and found the best parameters and best materials, and then applied in the coin cell size, and then transfer it to a single layers punch cell. And if everything works well, then we can have some additional external collaborators from other university or other industry. NPL also have very nice facilities, so we can just like move from beginning to the bigger. Yeah.
So is it like paint a picture for me? Is it like a chemistry set where you're mixing things in reagents in test tubes, or is it like making semiconductors where you're depositing very fine layers using light or some other technique?
Oh, from my lab, we are just working on because you can see I'm from Triple E department, so we are not do a lot of synthesis, but we are focused on the interface engineering using, for example, using some deposition method or using some ion implantation method. Yeah, this is our focus. But I know there's a lot of different group. We also have a lot of different collaborators. They just even from materials, from chemistry engineering, they can synthesize different kind of solid state electrolytes or different anode cathode materials. So this is a lot of ways to improve the performance. So we just have different approach, but the target is will be the same. So just to improve the performance, increase the energy densities, power densities, cycling performance, safety, etc.
It sounds very much like a collaborative effort. So is that something where you're collaborating with other departments in Surrey University, or is it at an international level where you're collaborating?
Yeah, we have some collaborator from different from like at Surrey, from the electrochemical engineering department, from chemistry department. I also hold a joint appointment at NPL, so we also have a lot of a large team working on the batteries. So especially for the battery calculations, I didn't explain today, but the battery calculations also a very important directions that will be used to understand the methods or used to develop some strategies to observe or predict the future performance.
I'm going to bring in my two colleagues now, Paul and Colin.
Yeah, good evening there. That's a very, very wonderful presentation.
I think you've got some questions, Paul, from the audience.
I do, yes. We've had quite a few questions coming in, particularly around the use of batteries and the manufacturing of batteries at the moment and going forward. So we've had a question in from Alan, actually from others, around the use and charging process of batteries, particularly at the moment and going forward. I suppose when you consider the development of batteries at the moment and the chemistry of them, certainly in the near future and the far future with solid states, when do you anticipate that EV batteries and EV charging will be down to, say, the minutes of charging time, particularly when you consider the use of people's real world environment, 20, 25 minutes, that sort of thing? I mean, you mentioned that solid state probably won't be able to charge faster, but do you imagine that one day that may happen?
So first, I'm very confident. Like we can based on the development of batteries, we can definitely reduce increase the speed of the charging, and also to reduce the charging time. So that's for sure. But it's also depend on like to which level. For example, from like several hours to 1 hour, I think that's definitely doable. But if you go to to 1 minute or even less, then that is probably need some dramatic changes. Not only you change the electrolyte, but you can also maybe you have to change the concept. Not only for example, the charging mechanisms. Right now, because this as I showed like in the slides, the rocking chair mechanisms, and you also need this is not like a ultra fast process. Some other candidates, for example, supercapacitors, that can be charged super fast. But for the batteries, if you want to provide a large energies, give the battery some time to allow the ion diffusion is necessary. So if we can further increase the ionic conductivities of the anode cathode electrolyte and the electron conductivities of the electrode materials, especially, and reduce the impedance of the resistance between the interface, etc. That's definitely can improve the capacity. And thinking about from the materials point of view, so I didn't go into deep, but for example, right now, all the batteries, you can think they have crystal structures, and in the crystal structures, they have some channel allow the ion diffusion. Right now, it's a 2D channels, and if you can make the channel larger and make it 3D, they can allow the ion diffuse, like more ion diffusing in the same times, which means like you can save the charging time. But and also we need to consider if we increase the charging speed, then that can also have a lot of side effect. For example, they can generate a lot of heat, thermal. So how to avoid this happens? And especially if we want to have some large capacity batteries, then and how to cooling down, how to design the cage, how to design the sensor, how to design the system to allow the battery charged like uniformly, not not just through one point and generating the heat from one point. So that is quite dangerous. So a lot of things from material point of views, from cell assembling skills, from manufacturing, from the software design. So a lot of things will combine together to achieve this. But definitely, I mean, if you think about the previous several years, takes like even 24 hours, right? Or even days to charge a large batteries, but now it already significantly reduced the time. So I'm sure that this can achieved but to some level.
Yeah, and I understand. I think it as we are able to increase the capacity and charging rate, the problems will no longer be the batteries themselves. It will be the environment that they're in. You know, if we are looking at very high rates of charge, can the grid connection that it's at cope, for example, and where's that source of energy coming from? It's no longer a problem for the batteries, it's the world around that. But as I suppose that's, you know, talking about that rocking chair problem, you fix one and there's another and you keep bouncing backwards and forwards. No, it's a very, very good point around thermal too, in keeping those going, to make sure that the environment becomes the problem and no longer, and the user no longer really, sorry, how we use them rather than just the batteries themselves.
Yes. And another point I also want to add, sorry. So actually, when we charge the batteries, we are not charged in a same speed. So if, for example, we can charge the battery very fast at the beginning, just imagine if the battery materials is you can think about, okay, it's a house. So at the beginning it's empty, so a lot of people can go very fast inside, so we can have a high fast charging speed. But later, if already a lot of lithium or a lot of people in a smart house, then especially have a very small channel, then we have to reduce the speed to allow the ions or the peoples to go in like smoothly. Otherwise, they can hit to each other or hit the wall. So that is the problems. So if we just want to charge to some levels, we can use a high current. But if we want to charge to a full 100%, then they have to reduce the speed a little bit.
I like that analogy. That's a very good. The people in the house is not one I've heard before.
Yeah.
Right? It's a good one.
Yeah, it's a brilliant answer. Thank you, Yolanda. Got another question here before I pass this to my colleague Colin. And it's one that a number of attendees have asked similar questions too, and I'm sure many more have been considering this, certainly of recent years and months. So the question from Alexander and others was to do with around the environmental impact of the manufacturing of batteries. And as technology develops, particularly the complexity and the elements that are required within them, do you see that, you know, the real world use of those batteries, particularly EVs, you know, potentially, as you say, for up to 15 years of lifetime going forward, certainly in our lifetime now, would you see that being able to mitigate the environmental impact of manufacturing those batteries? And as a side note to that, are we ever likely to run out of those chemical elements?
That's also very important point. Very nice questions. So yeah, if you look at the Earth, like the abundance of the lithium, and actually not the lithium. If you think the most expensive right now in the battery is the cobalt. That is very expensive. So, and we have very small amount of those resources on the Earth. So, if we that definitely could be a problem. If we're thinking about this market was like dramatically increase, so the resources will be a big problems. But there are a lot of groups, research group, or even companies. They are just develop some other materials, like to reduce the for example, reduce using the cobalt, or to change to a cheaper, more abundance materials. And lithium is also not very much. So right now, a lot of like companies or groups, they have developed the sodium-ion batteries as a backup. I think right now, even there already have some companies like can commercialize the sodium-ion batteries. Then that's so yeah, a lot of effort have been put on develop other type of batteries to like. And also another questions, I think another point you mentioned, like so after, for example, after 10 years, if the battery was the performance cannot be is good enough to support vehicles, then how to recycle those batteries? This is also a very important point. I think a lot of I also see some some reports, some news, some companies are already considering how to recycle recycle the battery. For example, in the batteries, they have different components. Some are metal, they can just take out from the batteries. Some are materials. They have a lot of technology that can take out the materials or can wash them. For example, if there are some like if there's some contaminations or side reactions, if they can remove those kind of like side product, then the battery can still run and increase the performance. They may not use it as the same. For example, they take out from the electric vehicle batteries, and they may not use the performance may not as good as the like fresh battery materials, but they can just use in some other low, like for example, large scale stationary energy storage. They can use in some other applications. That is another options. So I think in Europe, UK, Europe, like US, China, Japan, they already have some companies thinking about this and doing this now.
Yeah, it's a very rapidly changing industry. Particularly people are now thinking about the recycling and the chemistry that's used.
Yeah.
And I think it's fair to say, perhaps, one quick question on your view, this is more a question for myself to you, that the commercial side of the sourcing and manufacturing these chemicals will often be the winning reason for that being the adopted technology, not necessarily because it is the best and it charges fastest. It will always often come down to cost.
Yeah.
And is that how you see things going forward as well?
Oh, yes.
That's that's how it seems to be for the rest of the life. I'll pass over to my colleague Colin, who's got some more questions for you.
Yeah, thanks very much, Paul. Yonglun, quite a couple of questions that came out were really all concerned with timings, different aspects of timings. At the beginning of your presentation on one of the slides, there were a series of projections as to what might happen in terms of costs, energy density, and things like that, going out to 2035, 15 years. The fundamental question is, how realistic are those projections? Are they guesstimates? Are they what people would hope to do? Or are they based on a realistic trend that people have been able to follow? That's the first point. Before you answer that, I'll just throw in another one. A question arose, again, it's related to time. If you were to manufacture a solid state battery at a small scale, and for example, for safety reasons, it might be appropriate to put it in a mobile phone, which would cut down the possibility of ignition. Is that feasible in the short term, do you think? And if so, would it perhaps extend the life of a battery? Could it last longer than a conventional one?
Okay, thanks. So the first question is about for example, the current parameters of the batteries, and I think in one slide I just shows like the predictions or what's the requirement. So first, I think by the way, I want to explain this. Those parameters may not targeting like solid state battery. This is very general for general batteries. So the first question, how accurate or can we achieve these goals? For me, to be honest, it's a little hard to answer these questions. So because this goal have been when they set this goal or this target, they are considering a lot of things. As I mentioned, it's from materials side, from the lab skill, from manufacturing, a lot of things. So but that is the target for 2035, and we are quite confident at the lab level. That's definitely no problems. We are actually already a lot of research group. They already have some good publications showing that they can reach that goals. So which means like then how to transfer those strategies or the techniques from lab small scales to a large scales. So that still need a lot of input, I think. But the good things, for example, by comparing with previous goal we have set, for example, 2020s, maybe we compare with the 10 years ago, 10 years ago when we have a goal like at 2020s, actually we already achieved most of them. So it's a good thing. So actually it's quite convenient, like positive things. So for another second questions is, can we use instead of using in electric vehicles, can we use a solid state battery in like small devices, for example, phone, right? So if remember in one slide, I also mentioned like a thin film solid state battery, right? So that technology actually already commercial, and especially Japan, they have very nice technology. They can build a very nice thin film batteries using plasma, sputtering, not plasma, sputtering, making those kind of devices. And these devices can be used to powering the different kind of devices, but that is still too small for a phone. I have to see if, in my mind, actually, if the phones already is quite it need a like a punch cell, so that is still already quite big. But if we just make a small punch cell solid state batteries, I can see a lot of research group, they can already do this, and some companies, they can even make some demo. So that's for sure. And if we don't make a lot, if we use a thin film battery type technologies, we can reduce the thickness of the electrolyte, and we can using coating method, then the charging speed can further increase because we have less charging speed. Charging length. Diffusion length. Sorry.
Okay, thank you.
So where would you say in the world is leading on solid state batteries at the moment?
Right now, like I think still like US, China, Japan, Korea, and they are compared with relatively like they have some larger manufacturer, but the UK also did very nice on this. We have a Friday Institute. We have a lot of fantastic academics and industry collaborators working on the solid state batteries. Also very nice.
Oh, that's good to hear. Definitely, yeah. I think we're going to run out of time very shortly. Lots of questions came in from the audience, and we kind of grouped them together in a similar theme of topic. I guess from me, another question would be, when you're making these battery packs, you've got thousands and thousands of individual cells, and as the density goes higher and higher, is it a case that the weakest cell becomes the limitation of the whole pack, or is that somehow mitigated by some other method?
Oh, that's also a very good point. They come from the cell design to a packet design, and at the packet level, we will in engineering we put a additional system called battery management systems. So each cell, we try to make everyone same, but it's impossible. So some battery probably can, if we test it individually, some can charge faster, some cannot. Some have a larger capacity, some are not. But using the battery management systems, they have a control systems. They can just make sure all the cells can charge at the same speed, and sorry, not at the same, as a unit, they can charge like smoothly. I am not like expert on the battery management systems, but I know they have some additional functions to address these concerns.
And how does your work on the interface between the electrical and the biotechnology fit in with that?
Yeah, because my background is quite it's a little weird, because I did like electrochemistry and also electrical biologies. But yeah, there are a lot of for example, when I doing some implantable medical devices or wearable medical devices, we need it's integrated systems, need sensors, right? You need antennas, and also very importantly need a power unit. So right now in my group, we have several students working on how to make like, for example, implantable biocompatible batteries, even in the implantable bioelectronics or wearable electronics. So there are a lot of need a lot of background from, or details from, not only from the battery people, also from, and so need some the back experience from both sides. So we are also trying to work on those problems.
That sounds like a very interesting thing to be involved in, and I'm guessing a new challenge every day.
Yes.
And that's all from me pretty much today. So it's really just to say thank you very much, and to say that Solid State Batteries was presented by me, that's Nigel Ward, And our guest today was Yunlong Zhao from the University of Surrey. The event creator was Tim Brown, assisted by Peter Mansbridge. Question masters today were Colin Cunningham and Paul Cole. The producers were Colin Cunningham and Julie Hudson. And this has been an IET production brought to you by the volunteers of the IET in Surrey. Thank you very much for watching.